Hello everyone, welcome to another riveting episode of Dave Does Math from Home. At this point, I'm sure that everyone is pretty sick of doing derivatives using limits of difference quotients. It is a process. It is long. It's not difficult, it's just sort of a lot, and it's not very rewarding. So I have excellent news for everyone. Today, we're going to talk about derivative shortcuts. We're going to skip some steps. We're going to make this process easy so that when we start doing derivatives of more interesting functions and it gets really extra super hard again, you will have had this break. And you won't hate me. That's the goal. So, we're going to start with some of the easy stuff. I think in the past we have done functions like x squared, and we know that the derivative there is 2x, and we should be able to look at something like 3x and know that the derivative there is 3 because this is a straight line with a slope of 3, so the slope should always be 3. That's what that means. So, one of the first and most basic rules of derivatives is, it has a fancy name. I think it's called the sum and difference rule or something. I'm not interested in the fancy name. But the gist of it is, if we create a new function, if I start doing something else, if I say y equals x squared plus 3x, I don't have to treat this like its own entire separate thing. I can look at this and say, well, this is x squared from here and 3x from here, and I know the derivatives of those two things, so I should be able to say that this is 2x plus 3. And again, not interested in the fancy name of this property. I refer to this as addition is safe. So, if you have a function that is the sum or difference, subtraction is safe as well. If you have a function that is the sum or difference of a bunch of different pieces, or a bunch of different terms, we can look at each of those terms individually to find a derivative. You can just take the derivative of the x squared piece and get this, and the derivative of 3x piece and get this, and then you're all set. You don't have to worry about, like, when we add this to this, it's not going to influence the derivative of this piece. That might seem like really intuitive or like obvious to some of you. Some of you might be thinking, why is he even making a big deal out of saying this? And the answer is, multiplication and division are not safe. If we try to create a new function that is x squared times 3x, the derivative of this is not 2x times 3. The derivative here is something else entirely. So it's important to state explicitly that addition and subtraction are safe, to highlight the fact that multiplication and division are not. So this is our first little shortcut, addition and subtraction safe. That's going to be handy. The second thing that we should talk about in this section is coefficients. We know that the derivative of x squared is 2x. What can we say about the derivative of 4x squared, do you think? I think this is x squared plus x squared plus x squared plus x squared. And if addition is safe, the derivative should be 2x plus 2x plus 2x plus 2x, which looks a lot like 4 times 2x. Which is nice because we can pretty much just ignore the 4, take this derivative of the x squared to get this 2x, and then just multiply that by 4. So this is the other thing I'll say about this. Coefficients are safe. Addition and subtraction are safe. Coefficients are safe. This is an idea that's going to come up over and over and over again. This is a very important property. And again, it kind of seems like on some level it should be intuitive and obvious and like not something that's worth like spending a lot of time talking about, but we're going to come back to this so many times throughout the rest of the semester and even further in Calc 2. This comes back a lot in Calc 2. That it deserves to be said and repeated. Coefficients are safe, addition and subtraction are safe. Multiplication and division are not safe. We're going to get to those in later sections. There's a couple very interesting properties, sort of techniques that we can use to find the derivatives of functions that are products of other functions. It's very interesting. There's also the other thing we can do with two functions is we can put them inside of each other, create a composite function with one function inside the other. That is also not safe, in that there's a special rule that you need to use to find the derivative of a composite function. You can't just take the derivative of the outside and the derivative of the outside and put them together. It doesn't work like that. So, addition and subtraction coefficients are safe. Multiplication, division, and composition are not safe. These do not work in a really straightforward, intuitive way that is obvious. They work in a complex, sort of bizarre way that is not obvious, and we need to spend some time talking about how to do derivatives of multiplication, division, composition. But we'll get to that later. That's for later sections. I'm just writing it here to highlight the fact that addition and subtraction and coefficients are safe. So, let's talk about something else. I know that the derivative of x squared is 2x, about x cubed. So I want the derivative of x cubed. Let's find that. G prime of x should be the limit, as h approaches 0, of g of x plus h minus g of x all over h, which will be the limit, as h approaches 0, of x plus h cubed should give me x cubed plus 3x squared h plus 3x h squared plus h cubed. This is, I'm kind of using a shortcut here. This is from something called the binomial expansion theorem. It's like a shortcut for if you have an a plus b squared or cubed or to the fourth, or an x plus h squared or cubed or to the fourth. Binomial expansion theorem sort of gives you like a blueprint of what the expansion of that should look like. And when you cube something, it looks like this. First term cubed, last term cubed, 3 of each of the mixed terms. So there's an x squared h and an hx squared. So all of these things are third degree terms, just of different combinations of the variables. G of x is x cubed, and it's also over h. So my x cubes will cancel, as we expect them to, and then I can divide out these h's, and I get the limit is h goes to 0. This h cancels entirely, gives me 3x squared. One of these h's cancels, so I have a 3xh, and one of those h's cancels, so I have h squared. Now that the h from the bottom has canceled itself out, I'm safe to execute plan B, where I can take the limit as h goes to 0, and I'll get 3x squared. This is the derivative of x cubed. 4x squared. So that's convenient. And we can sort of check this graphically if we like. X cubed looks like this. So it's interesting to note that except for at this point right here, where it sort of flattens out, it is always positive. And if we want a function that is always positive and like steeply positive, less positive, 0, positive, steeply positive, we get something that looks like a parabola. So this checks out. Let's do another one. How much time am I at? 10 minutes. Okay. Yeah, we have time for another one. We're good. Alright, what's the next letter I should use? Let's move on to y. Let's say y equals x to the 4th. I want to know what y prime is. So again, y prime is the limit as h goes to 0 of y of x plus h minus y of x over h. So the limit as h goes to 0 of y of x plus h means x plus h to the 4th. So I need to use that binomial expansion theorem again. And I can, if you're really curious about the particulars of how the binomial expansion theorem works, that is definitely something you can look up online. It should be pretty readily available. I'm not going to spend a lot of time talking about it in this video. I'm just going to use it. You can trust me that it works, so you can look it up yourself. But x plus h to the 4th is going to give me x to the 4th plus 4 of these. It'll give me 6 of the middle term, and then back down to 4, and then 1 of those. So 1 of each of the sort of by themselves terms, 4 each of the 3 and 1 terms, 6 of the 2 and 2 terms. Oh, I need to subtract y of x, so minus x to the 4th, and then it's all divided by h. So, once again, these pieces cancel. I can take the h out of what's left. Now we'll get the limit as h goes to 0 of 4x cubed, 6x squared h, 4x h squared, and 1h cubed. So here's what's interesting about this at this point. All of these things have h's in them, so when I execute plan B and set h equals 0, I'm just going to get the 4x cubed. Hopefully, at this point we are starting to see a pattern in terms of what these derivatives look like. X squared turned into 2x to the 1, x to the 3 turned into 3x squared, x to the 4 turned into 4x cubed. I'm going to let you see if you can puzzle together this pattern while I erase the board and prepare us for part 2 of this video.